Hi everybody, welcome to section 3.2. That's on measures of variability. Another term for variability is spread, and yet another term is dispersion. All of those terms refer to how closely together the data points are clustered. Are they all close together or are they really far apart? I want to show you two data sets we're going to work with in this section. The first one is waiting times at a bank. These are all in minutes. So these are all in, so there's, I guess, 11 customers who went to a bank and they kept track of their waiting times. And then the other data set we're going to look at is we've got two cities and gas prices per gallon in each of those cities on a given day. So 10 different gas stations, they recorded their gas prices there. So we're going to look at a few different measures of variability. The first one is the range. The range is the difference between the maximum and the minimum data points. It's just calculated as the maximum minus the minimum. In Excel, there's not a range function, so you just have to calculate the maximum and the minimum. And there are functions for that. So if we want the maximum, and I'm going to put labels in here, which is what I would very much like for you to do, because that goes a long way toward making your spreadsheets look professional. So I want to do that on the waiting times. So let's find the maximum and the minimum. The function for the maximum is max. And you just select your data. It tells us that the maximum data point is 10.49. And to get the minimum, it's min. But if you forget what the function is called, remember you can always go back and look at the FX button. And you can find it somewhere in here under one of these categories of functions, or you can always use a search engine. So let's pick the minimum. We'll select our data, and we get 0.5. So the range is the maximum minus the minimum. Okay, and I'm referring to those cells rather than typing in 10.49 and 0.5. That's good form to have in your Excel spreadsheets. The one benefit of that is that if you realize one of these numbers should have been different for some reason, if this was supposed to be 1 instead of 0.5, it automatically updates it. Whereas if you type in just 10.49 minus 0.5, it won't do it. Another option, and I want to point this out because I know some of you haven't used Excel all that much yet, you can put that whole thing directly into one cell. So you can do equals max, select your data, minus min, select your data, and you can do that all in one step. Okay, so for this data set, the range is 9.99 minutes. And I do want you to label that in the correct units. And I'll go ahead and write this out so you have it in your notes. One other thing about range before we move on it's not incorrect to say that your data ranges from 0.5 to 10.49 minutes. However, when they ask for the range, they're asking for the difference between the maximum and the minimum. All right, next, the interquartile range. So this is, if you pick apart this term, this is the range. Inter means between the quartiles. So this is the range between the quartiles. So this is the difference between the first and third quartiles. Or I'll actually write this as third and first, because technically this means the third minus the first. Interquartile range is abbreviated as IQR. And so it's just Q3 minus Q1, and that's your IQR. In Excel, there's, again, not a function directly for the interquartile range. So you just have to calculate it by finding the quartiles separately and then subtracting them. And if you remember, we did quartiles in the last section, so I'm confident you remember that. But let's find Q1 and Q3. We'll be consistent, putting the top number first. So quartile.exe, select our data, and we have to type in which quartile we want, and we want 3. Q1 is, again, quartile.exe. Select your data, and this time we want the first. So our interquartile range is Q3 minus Q1, which is 2.9. So 8.37 minus 5.47. 37 minus 5.47. And if you remember, I said there's no reason for you to use a calculator in this class. I want us to use Excel for everything. So we get 2.9 minutes. All right, so that's how to calculate the interquartile range. That is sometimes used as a measure of dispersion. For this next part, I want to just use a basic data set, and I want to do these problems by hand, just so you get an idea of how this works. These formulas, I think doing them by hand a little bit will give you a little better intuition about what they're doing. I remember they did when I was first learning this material back, long time ago, back in the last century. And when I say I want you to do the problems by hand, I'll show you how you can do them by hand in Excel. But first, I just want to write it all out. And I'll apologize in advance. I have this mouse pen, which is really, really great and has been really handy lately, but it's a little unwieldy. It's hard to write neatly with it, and I can't write quickly with it. It just rebels if I do quickly. So, a little bit of review here. If you remember, X bar stands for the sample mean. So we need to find the mean of this data set. So to start with, and I went ahead and put these in here. So the average here was 20. I made that data set up so it had a nice round number. And we're going to label that as the mean. So this formula, the first thing is the sum of squared errors. This itself is sometimes used as a measure of dispersion. It's a little more important because it's a step along the way to calculating some other stuff. So this is, when we say errors, we mean how far the observation is from the sample mean. So we're going to take every observation, subtract the sample mean, and then we're going to square it, and then take the sum. So that's what this formula is telling us to do. It's telling us to take every observation, subtract the mean, square those results, and then take the sum. So we got up here that our x bar was 20. So to get the sum of the squared errors, we're going to take the first observation, 18, and we're going to subtract 20 and square it. And then we're going to add that to 21 minus 20 squared, because that's our second observation. And then we're going to do that all the way through. So 19 minus 20 squared and 25 minus 20 squared. Seems like I missed one. Oh, I did. I missed 17, but it doesn't matter what order you do these in. Three, four, five. Yep, they're all in there now. So we've got our differences. So 18 minus 20, that's negative 2. And then we're going to square them. And this is 4. 21 minus 20 is 1 squared, which is 1. And we're going to keep going just like that. And this is 1. This is 5 squared, which is 25. And 17 minus 20, that's negative 3 squared, which is 9. And then when we take the sum of all of those, that's, let's see, this is 5 and that's 10. So 15 plus 25 is 40. So that's the sum of the squared errors. So that's our first step on the way to calculating the sample standard deviation, which is really the important thing. The sample variance is another measure of dispersion. Again, it's not as important as the standard deviation, but once we've got the sum of the squared errors, the sample variance is very easy to calculate. So S squared is just the SSE, because that's what this is, divided by n minus 1. So if you remember what the symbol n stands for, that's the sample size. So in this case, we've got 1, 2, 3, 4, 5 observations. So the SSE is 40, and N is 5, so we're going to divide by 4. So 40 divided by 4 is 10. And then our sample standard deviation, this is the important measure. And I'll talk in just a second about what it means. But S is just calculated as the square root of S squared. So in this case, it's just the square root of 10. And I definitely don't expect you to know what the square root of 10 is off the top of your head. So we can do this in Excel. Equals SQRT is the function for square root of 10. And that is 3.16. So for now, we'll just say 3.16 is good. Okay? I always want you to use at least 2 decimal places in your answers. And by the way, I want you to round them correctly. Don't just lop off. So if you're rounding this to 2 decimal places, that would be 3.16. If it was 3.165, that would round up to 3.17. So I am going to be strict about that. Rounding numbers is one thing you should definitely be able to do as business majors or minors. So that's the sample standard deviation. I'm going to come back in just a second and show you how to do these things in Excel. Let me tell you what the sample standard deviation actually is. It's essentially, you can think of it as the typical distance. If you take that term standard deviation and pick it apart, standard means typical. Normal is another word, but in a class where we do the normal distribution, we shy away from using that word. But so I say typical, and deviation means distance. So this is the typical distance of observations away from the mean. It's not correct to say it's the average distance. But if you look at what we've done, we found essentially the distances of all of the x's of all of the observations from the mean. We squared those. We divided by almost the sample size. So at this point, when we do this, this is almost the average squared distance. And then here we take the square root. So it's, if you suspend order of operations for just a second, this is essentially the mean distance. But we can't suspend order of operations. But if you think about it as practically the mean distance, you'll be thinking about it the right way. So if you had another data set where the observations were further away, that would obviously have a much bigger standard deviation. So let's go over, let's do this part actually, for lack of a better way to put this, by hand using Excel. So it's not exactly by hand, but we're not going to use the functions just yet. All right, So we got the mean of 20. So the first thing we're going to do is we're going to take each observation. We're going to subtract the mean. And if you remember, I think you probably did this back in your 111 class. If you hit the F4 button, or whatever it is on a Mac that's equivalent, it'll put these dollar signs in here, which will fix this cell reference so that when you copy it down, it'll always refer to this cell. This is another one of those things that is good form to have, and so I want you to get in the habit of doing it that way. So yes, you could type in 20 and it would work. You get the right answer. But it's a good habit for you to get into, to refer to the cells, because as I mentioned earlier, if you were to change one of these observations, you want it to update everything automatically. That's one way that Excel helps with efficiency. And we're going to go ahead and square these in this step. So we've got our data point minus the mean, and we're squaring the result. And then I'm going to copy this all the way down so I don't have to type it again. So just like we did before, I'm going to move my mouse until the plus changes to there. Okay, so you see it change from the arrow to the big plus with the double-headed arrows, which is not what I want, to this little skinny plus. That's the one I want. So I'm going to highlight all the way down, and I always check and make sure it's referring to the cells I want it to refer to. All right, and we're going to be in the habit of always labeling things. So if that's x, this is x minus the mean squared. I've not found a good way of putting those symbols in here, but I want you to use correct symbols, not wherever you possibly can. So in a Word document, you can copy the symbols I'm putting up on the Canvas site for you to copy. And if you're doing anything by hand, I want you to use correct notation. Here in Excel, I've not found a good way to use that X bar. But anyway, so we've got our x minus the mean squared. And then this was just our square root of 10 there, so I'm not going to keep that. So then we want the sum of those squared error terms. And to get that, I can just use the auto sum. And that gives me exactly what I want. Always verify. And then we're going to divide by the sample size. I don't mind if you just count 1, 2, 3, 4, 5 here. If you want to see how to find the sample size, though, you can just do the count function. Which comes in handy sometimes. So our s squared is going to be our SSE divided by our sample size. And we get 8. And so our S is going to be, oh wait, it's not divided by that, it's divided by that minus 1. Yep, don't forget the minus 1 in the denominator. And don't forget that you need parentheses there too. So that gives us 10. And then we get for our standard deviation, we just do SQRT of that value. And always referring to the cell rather than just typing in the value. And we get our standard deviation of 3.16. And that's what we got before when we did it by hand. So this is doing it by hand using Excel, for lack of a better term. Now, there are direct functions for the variance and for the standard deviation. Here it's VAR. Now there's different ones, but the one we want is this one. This is variance based on a sample. And we want to pick our data. And this verifies that we got the right answer when we did it by hand. And similarly down here, you can get a sense of how important standard deviation is by looking at the number of variations of it that are available. So the one we're using is the sample standard deviation. And if we pick our data, we get 3.16, which is exactly what we got before. Another benefit to referring to the cell rather than typing in the values is you don't get round-off error. And I want you in this class to be very, very careful with round-off error, because that can add up quickly, especially if you're taking values, if you're doing a calculation and then rounding it and using that in another calculation, round-off error gets really bad really fast. All right, so that's the standard deviation. The coefficient of variation is a calculation that can be really useful. Coefficient of variation allows you to compare standard deviations across groups where you have different scales. It's calculated as S, or the sample standard deviation, divided by the sample mean. It also works for the population standard deviation and the population mean. But this is what we're using it for right now. So, and then you convert it to a percent. The interpretation for the coefficient of variation is it's the standard deviation as a percent of the mean. So by dividing the standard deviation, one thing I want to mention up here is that the standard deviation, not the others, but the standard deviation is in the same units as the original data. Okay, so again, that's not for the variance or the sum of the squared errors, but because we take the square root here, this brings it back to the same units as the original data. So if you're calculating over here the standard deviation of this data, we get 2.84. This is 2.84 minutes. Okay, so you should report the units here with with the standard deviation, not with the variance or the sum of the squared errors. All right, so back down here, so when you do this division, you're dividing, in this case, minutes by minutes. These are both in the same units. So you divide out the unit. And so you're left with a percent. So let's look at an example, a prime example where this is a useful thing to do. So if you want to compare which one's more spread out between ACT scores and SAT scores, those are on two different scales. So you can compute the coefficient of variation for both of those and see which one is larger. So for ACT scores, the coefficient of variation is the standard deviation, which is 5.8, divided by the mean, so 20.8. So 5.8 divided by 20.8, and I'm going to add a sheet just for these calculations. So 5.8 divided by 20.8 comes out to be 0.2788, and I want you to convert to a percent. Oh, I was in the wrong cell when I clicked percentage. And let's round those to 2 percentage decimal points, so 27.88%. And for the SAT, it's 211, because it's that standard deviation, divided by its mean of 1051. So 211 divided by 1051 is 20.08%. And then because the ACT has the larger, this one has more variability. You can tell I meant for that to be more variability. All right, so now let's look, just to kind of sum this up here, let's look at our gas prices. Let's compute the averages. And I'm adding a column so I can put labels in. So average of those gas prices, 2.21. And I made this data set where these both have exactly the same means. And so you can see that. But let's look at the range. So the two key measures that are relevant here is the range. So let's do the maximum minus the minimum. And this tells us that we have a range of 8 cents. So that means the difference between the largest and the smallest gas prices was 8 cents. And we can do the same thing over here, or we can just copy it over. And we get 50 cents. So the maximum there is $2.49, and the minimum is $1.99. All right. And I want to make sure I made a small error here, and I'm going to fix that. So if you're not careful, you can include the mean in your calculations, which is not what I wanted to do. I still got the same answers, but it is important that you're referring to the right cells. One thing I've done in the past that helps sometimes is draw a line, and that kind of can keep you straight about what's what. So let's look at the standard deviation. So stdev.s, and we will highlight our data. Copy it over, and always make sure we're getting the right cells in there. So this one has a standard deviation of only about 3 cents, whereas this one has a standard deviation of almost 15 cents. And I'm going to go ahead and write this as a dollar amount. Let's go ahead and do the interquartile range as well while we're here. So we're going to do the third quartile. So quartile.exe. All that data, comma 3, minus quartile.exe of all that data, comma 1. And I'm going fast here for the video, but you can pause it, remember. So we get an interquartile range here of 6 cents. And over here, we get 21 cents. So each one of these measures points to City B having a larger spread in their gas prices. And the reason we care about that is, in this case, if you think about it, the implications of this, if you're in City A, it really doesn't make much difference where you buy your gas. You're going to get the same price. Within 8 cents, or typically even within 3 cents. But in City B, it might be worth it to shop around because you've got a range of 50 cents, and that can add up quickly when you buy multiple gallons of gas. So here I would say, so if you're writing up your answer, I would say for City A, the range is 8 cents. The standard deviation is 3 cents. And the interquartile range is, I forget what it was, 6 cents. For City B, the range is, I think we said 15 cents. The standard deviation deviation, I'll check. Oh, the range was 50. The standard deviation was 15. And the interquartile range is 21 cents. Each of these measures is bigger in city B, indicating city B has more spread in their gas prices than city A. All right, one more thing and that's it for this lesson. And that's sample variance and standard deviation versus population variance and standard deviation. So the computations we've been doing are for the sample, and that's the way it's going to be for the course, because that's, practically everything you're going to do is going to be for the sample. The population formulas are almost exactly the same. The only difference is that in the population variance, you don't subtract 1. And I'll post a video that explains that if you want to see it. And I hope some of you will watch it. And it'll explain why, why the difference is. The important thing here is to notice the difference in notation. And I want you to, you need to know at least these two pieces of notation, the sample standard deviation and the population standard deviation. Because later in the course, there are going to be formulas where you plug in one or the other of those. And you're going to need to know the difference between them. So pay attention and write down in your notes that the sample standard deviation is S and the population standard deviation is sigma. So often the population values are Greek letters and the sample values are regular, those aren't Roman letters, whatever they are, our alphabet that we use. All right, so that's it for this lesson, and if you have any questions, please feel free to reach out to me.